In the last lecture, we saw the initial reactions of Grignards with ketones, aldehydes, formaldehyde, which was the one carbonaldehyde, and carbon dioxide. And the mechanism for that was fairly straightforward in terms of the nucleophile just simply attacking the carbonyl, forming the alkoxide ion, and then reprotonating. And so, for example, if we took a CH3 minus MgBr plus as a Grignard and we reacted it with, let's say, formaldehyde, the CH3 minus would come in, attack the carbonyl, the pair of electrons, the double bond would move to the oxygen so that we would form our carbon-carbon bond and then form the alkoxide ion, and then in a second step we would add our H plus H2O to form the final product. And in essence, the carbon that's attached to the OH was the carbonyl carbon, and then we've added this alkyl group to that carbonyl and formed what was the carbonyl carbon methyl group bond in this case. Well, when we react a Grignard with CO2, with formaldehyde in this case, with a ketone, or with a regular aldehyde, we simply get the addition of the alkyl group, and then after protonation get the alkoxide. Well, after the protonation of the alkoxide, get the alcohol. There are two other reactions, though, where you add Grignards to other carbonyl functional groups, and the reaction goes by a different mechanism. And so that the first one is what happens when you react Grignard reagents with esters. Well, what happens is that if you take and react a Grignard, and I'm going to make this a specific Grignard in this case, CH3 minus MgBr plus. And actually, I'm going to rewrite this whole mechanism on the next slide so it's relatively straightforward. So if we take our Grignard, our CH3 minus MgBr plus, and we react it with a simple ester, okay, in this case, let's react it with this ester. What's going to happen is we're going to get the same first step in the mechanism. Our carbon is electrophilic, the CH3 minus comes in, adds to the carbon, the double bond of the carbonyl goes to the oxygen, and so we form an alkoxide, and then we've added our CH3 group, and then we have our O and our CH3 group here. Now, esters are a little bit different than aldehydes or ketones from the standpoint that we're going to see later on, much later on when we talk about carbonyl chemistry, that whenever you add a nucleophile to a carbonyl carbon, this carbon-oxygen bond is stable. And so what the molecule is going to want to do is to bring this pair of electrons back down and reform the carbon-oxygen double bond. When we do this reaction with aldehydes and ketones, we either have hydrogens or alkyl groups attached to the carbonyl. The CO2 is a little bit different, but it reacts much the same way. So when you have the hydrogen or alkyl group attached to the carbon, this molecule would actually like to do that as well. It would love to bring this pair of electrons back down and reform the carbon-oxygen double bond. But in order for it to do that, one of these groups would have to leave. And if we looked at the periodic table, and down here I'll write a little periodic table, we'd have a hydrogen, and then we'd have our carbon, oxygen, nitrogen, fluorine. If you look at the periodic table, we know that that basicity increases as we go from right to left. If we go back to last semester and remember, how would leaving group ability go on the periodic table? What would be the trend? We would say that leaving group ability increases as we go from right to left, because remember, leaving group ability is indirectly proportional to basicity. The stronger the base, the poorer it is as a leaving group, to the point that hydrogen and carbon never act as leaving groups because they are such strong bases. And so if you add an alkyl carbanion to an aldehyde or a ketone, once you form this alkoxide, it turns out that all three of the groups that are attached to the carbon are poor leaving groups, and they never act as leaving groups. So the molecule is stuck in this position as the alkoxide, and it has to wait to be protonated to finish off the reaction. But when we use esters, or the next reaction, if this OCH3 group is a halogen, it could be a leaving group. Okay, it's not a great leaving group, but the key is that it could leave. And so what happens is that for this molecule, when I bring this pair of electrons down, neither of these two alkyl groups are going to leave, but this group can. And so the difference in the mechanism is that when this pair of electrons moves down here, instead of the molecule being stuck like it was up here, this OCH3 group leaves, so I lose that, and then I end up forming a ketone. Okay. Now this different mechanism only occurs when the carbonyl group has a potential leaving group added attached to it. So the ester is one of these leaving groups. Now, the problem in this reaction is if I was to add one equivalent of Grignard to this ester, some of the CH3s would add here, and then after this loses a CH3, I form a ketone. And so some of the CH3 would add to form the ketone, but then some of the CH3 would attack this ketone to form a tertiary alcohol. And so in order to avoid a mixture of different products, what we do is not add one equivalent, we add two equivalents of methyl of CH3 minus, so that as soon as that CH3O minus leaves, we end up with the second equivalent of Grignard adding to the ketone, and then we form our tertiary alkoxide. Now, as much as this molecule would want to bring a pair of electrons back down here, it can't, because all three groups are either alkyl groups or hydrogens. And so in this case, we would wait around and then add H plus H2O in a second step to form the final product, which would be, in this case, tertiary butyl alcohol. So when you react a Grignard with an ester, you have to react two equivalents of the Grignard, and you make a product where two of the alkyl groups in the final alcohol came from the two equivalents of Grignard. So if I come over here and I circle this Grignard and I put a square around that methyl group, the first methyl adds to the carbon, then the pair of electrons moves down and we kick off the methoxy group here. That leaves us then having added one methyl group, and then the second methyl group comes in, adds to the carbonyl. So our final product has one of the alkyl groups from the original ester and the other two from the two equivalents of Grignard that added. And so reacting Grignards with esters is a good way of making tertiary alcohols where two of the alkyl groups are identical to each other. And if we go back, that's what I'm showing in this particular mechanism here with the more generic R's, R primes, and then R double primes. Okay, so that is a different mechanism when you react Grignards with esters, because with an ester we have this OR group, which is a potential leaving group, and actually will leave in this mechanism. Okay. Same thing happens when you react a carboxylic acid chloride with a Grignard. You might say, well, what's a carboxylic acid chloride? Carboxylic acid chloride is when you have a carbonyl attached to a chlorine. And we'll talk more about this functional group a little bit later on. But if you have a carboxylic acid chloride and you react it now with our two equivalents of Grignard, we're going to have the same mechanism occur. In other words, the first methyl carbanion will attack that carbon and will form an alkoxide ion. And now for this molecule, again, the molecule really wants to reform this carbon-oxygen double bond because it's so stable. So it'll want to bring this pair of electrons down. In this case, there's no question chlorine is a good leaving group, and so the chlorine will get kicked off so that I'll lose the chloride ion, and now I will form the ketone. And now the second equivalent of Grignard now comes in and adds to that carbon. Pair of electrons gets kicked off there, so that, or gets moved up to the oxygen, so that now I form my tertiary alkoxide, where again two of the methyl groups have come from the Grignard, and the other methyl group in this case came from the original ester. And so now I wait until somebody dumps in some acid, and then I form my final product, which is the tertiary alcohol. Okay. So when you add Grignard reagents to carboxylic acid chlorides or esters, the first important thing is we need to add two equivalents of the Grignard. Because chlorine and the OR group are potential leaving groups, they will actually leave in the mechanism, which makes it a different mechanism. The net result is that we end up with tertiary alcohols where two of the groups are identical because those two alkyl groups came from Grignards. Okay, so it has a different mechanism because of the presence of the potential leaving group. Okay. Now, the last reaction that we'll talk about of Grignards for the moment are reacting Grignards with epoxides. Remember epoxides from last semester? We made epoxides by taking alkenes and reacting them in a one-step mechanism with a peroxy acid. And this then gives me an epoxide. Last semester, what we did was we reacted the epoxides with acid and a nucleophile, either H+, maybe Br-, so HBr, HCl, H+, H2O, or H+ and an alcohol. And what happened last semester was that this oxygen would be protonated by the acid so that I would form an oxonium ion. which the oxygen's not happy with a positive charge. So the way we actually wrote this structure was we wrote it sort of in this form, where we put the delta plus charge down on those two carbons and they shared it. This was reminiscent of what kind of triangular intermediate from last semester? How about a bromonium ion? Well, then our nucleophile, whether it be bromine, chlorine, water, or alcohol, would then have a choice of which carbon it was going to react with. Was it going to react with carbon A? Was it going to be reacting with carbon B? And remember that we said this mechanism was SN1-ish, at least from the standpoint of the nucleophile reacting with the carbon with the most delta positive charge, which this carbon looks like a secondary carbocation. This carbon looks like a primary carbocation. And so the nucleophile would have added to carbon A, and then the pair of electrons would have, the carbon-oxygen bond would have broken, so that if in this mechanism we always added the nucleophile to the more substituted carbon, and the least substituted carbon would get the OH group at the end of this mechanism. Now usually we added H plus H2O so that we got two OHs and we made our glycol. So that was last semester. And because I protonated the oxygen, I made this go through sort of an SN1 mechanism, at least in terms of the regioselectivity of the nucleophile for whatever carbon it was going to add to. In both cases, it was backside displacement, so it still had SN2 characteristics because the nucleophile and the OH group always added trans. Okay. Now, that's a long-winded refresher from last semester. And if you said, if you're saying, well, I remember all of that stuff, good. I have a feeling you're in the minority on that, but that's what we did last semester. Now, when we open up epoxides with Grignards, and I'll just talk about Grignards at the moment, the CH3- is not a weak nucleophile, it's a strong nucleophile. And so therefore the mechanism of opening the epoxide up is going to change. We didn't talk about base catalyzed ring opening last semester. We only talked about acid catalyzed ring opening. Well, base catalyzed ring opening is still going to occur by backside displacement. So the nucleophile and the OH group are still going to end up trans. But now the mechanism is going to be SN2-like in its regioselectivity. In other words, which carbon is the CH3 going to attack, A or B? Well, remember, what is important about SN2 mechanisms? They're based on sterics. Why does a primary alkyl halide undergo the fastest SN2? Because it's the least sterically hindered around the carbon with the halogen attached. Why don't tertiary alkyl halides undergo SN2? Because they're too sterically hindered. So SN2 is based on steric hindrance. SN1 is based on the stability of the carbocation. So now I've got an SN2 mechanism. So which carbon is the CH3- going to attack in this case? The least sterically hindered one, which is B. So the CH3- is going to come in. It's going to attack B because that's the least sterically hindered. And so when the CH3 comes in and attacks that, pair of electrons moves up to the oxygen so that, or pair of electrons moves to the oxygen so that I form an alkoxide. And now my CH3 added to carbon A. Okay, same problem as before. I have to wait around until I dump the acid in, and then when I dump the acid in, we now get our alcohol. So the nucleophile will attack the least sterically hindered carbon of the epoxide, and that's because it's a strong nucleophile and it's going by an SN2 mechanism. Okay, so when you use Grignards, when you react Grignards with epoxides, the Grignard is going to attack the carbon that's least sterically hindered to open up the epoxide. Okay, and that's an important reaction. And I'll point out one other thing when you react Grignards with epoxides, and that is that in all of our other Grignards, and let me go back here to this one just as an example, the Grignard, the CH3 group in this case, they end up added to the carbon that was the carbon of the carbonyl group. Okay, that's when you react a Grignard with a carbonyl. When you react a Grignard with an epoxide, notice that the Grignard ends up attached to the carbon that's next to the carbon with the oxygen attached to it. Okay. The carbon with the oxygen attached to it in the Grignard with carbonyl, it was the carbonyl group, but now the Grignard is attached to the carbon next to the carbon with the oxygen. And that's if you had two Grignard products and you knew where what the Grignard part was, you would know that you reacted an epoxide with that Grignard because the alkyl group is attached to the carbon next to the CO group. Whereas if it was a Grignard with a carbonyl, the Grignard ends up attached to the carbon that's attached to the oxygen. That'll become important a little bit later on. Okay, so we can react Grignards with aldehydes, ketones, carbon dioxide, esters, acid chlorides, and epoxides. And there'll be more reactions as we go throughout the rest of the semester, but these are just the ones we're going to start with. Now, in your textbook, they talk about the side reactions of Grignards. A side reaction, you know, from lab is kind of a unwanted reaction. So one of the side reactions that you can end up with is you can end up, if you're not careful, killing your Grignard. For instance, when we make a Grignard, if we take our alkyl halide and we react it with magnesium metal, the Grignard I'm trying to form, the carbanion I'm trying to form, is not only a strong nucleophile, but it's also a strong base. Well, the issue here is that if it's a strong base, it'll deprotonate pretty much anything that it can. When we do this reaction in the lab, we have to avoid things like water. Actually, we should avoid things like CO2 because, as we saw in the last lecture, CO2 will react with a Grignard to make a carboxylic acid. We should avoid things like carboxylic acids because they could be deprotonated by this strong base. We should watch out for things like amines because NHs will be deprotonated. We should avoid things like alcohols because they'll be deprotonated. The textbook talks about kind of avoiding even terminal alkynes because the terminal alkynyl hydrogen can be deprotonated. So this as a strong base will deprotonate any one of these species. So if I'm making the Grignard, got to dry the glassware. In my lab, if I'm making Grignards, and I don't usually make Grignards, I make organolithium compounds, I got to avoid CO2, which means I have to do the reaction not in air, but in something like argon gas or purified nitrogen to keep the CO2 out. I need to make sure that my molecule doesn't have any of these functional groups in it, because if it has them, they will be deprotonated the minute that I make the Grignard, and I will kill the Grignard that I'm trying to make. Well, you can actually take advantage of this reaction to do something that's a little bit specialized, but you can replace hydrogen with deuterium. Now, you'll see in your book sometimes molecules with a D attached to them. And then you'll try and look on the periodic table and realize there's no element D. Deuterium is an isotope of hydrogen that has a mass of 2. Remember, most of the hydrogen is hydrogen with a mass of 1. There's radioactive hydrogen, which is called, this one is called tritium, and it has a mass of 3. But the hydrogen with a mass of 2 is called deuterium. And so sometimes we'll replace a hydrogen with a deuterium in an organic molecule to kind of track that deuterium and see where it goes in the molecule. And the reason that we use deuterium is because it, in essence, has the same spatial characteristics of a hydrogen, i.e. it's the same size. And so it allows me to determine the difference, let's say, between this group and this group, or in this case in particular, this end of the molecule versus this end of the molecule now become different because one has a CH3 and one has a deuterium on it. But I can determine, or I can differentiate between these two carbons, and they basically have the same steric hindrance because the deuterium is the same size as a hydrogen. Now, that's not to say that deuterium doesn't affect the reaction, but that's beyond the scope of this course. So sometimes when we want to replace a hydrogen in a molecule with a deuterium, how do we do it? Well, we simply make our Grignard, so we would make our R minus MgBr plus molecule, and then we would react it with water where all the hydrogen's been replaced with deuterium. This is sometimes called heavy water. In nuclear reactors, they usually have water that's been replaced with deuterium, where the hydrogen's been replaced with deuterium around the nuclear reactor. At least if you had a water reactor, that would be the heavy water. So what happens is that the Grignard, we're deliberately putting the Grignard in the presence of something that will deprotonate, and it ends up then forming the carbon deuterium bond. And so, for instance, if I wanted to make this molecule over here so that I could differentiate this CH3 from this CH3, and why would you want to do that? Oh, I don't. Let's say you were doing free radical halogenation studies, and you wanted to tell whether or not the two CH3 groups, if you were to take propane and react propane with, let's say, bromine and light, and you wanted to determine whether or not the two methyl groups were reacted identical, what you might do is replace one of the hydrogens with deuterium and keep the other group as a CH3. What would you do? Put a bromine there, take the Grignard, make the Grignard out of it, dump in D2O, and you deprotonate it. And you deprotonate the D2O, and so you put a deuterium in there. So the idea here is that if you want to replace a hydrogen with a deuterium, you ultimately need to put a bromine for that hydrogen and then make a Grignard and quench it. The term we use is quenching with water. Only in this case you use heavy water. Okay. So that's one of the side reactions. The other side reaction that can happen when you do a Grignard reaction in the lab is what's called Wurtz coupling. And in Wurtz coupling, what happens is that the Grignard, so this is your minus with your MgBr plus, that the Grignard actually can react with the alkyl halide to couple those two carbons together to form a byproduct or a side product of the reaction. Now, remember we talked about the term coupling last semester when we brought two radicals together, two alkyl radicals, to make one of the products in the termination steps of free radical halogenation. That's the same type of coupling that we're doing here. So what happens is that if you have Grignard in the presence of alkyl halide, and remember you're trying to turn this alkyl halide into this Grignard by adding magnesium metal to it, if the two are together simultaneously in the reaction, the side reaction can occur. The side product kills my Grignard reaction because not only did I just lose a molecule of Grignard, but I just lost another molecule of potential Grignard. Typically, when we make a Grignard in lab, we'll take and put some magnesium metal, and then we'll use a solvent like diethyl ether. And then we'll slowly drip in the alkyl halide while heating the magnesium metal. Well, if we just dumped in all of the alkyl halide, as soon as the alkyl halide got converted to Grignard, it would undergo this coupling, this Wurtz coupling reaction. So in general, what we try and do is we try and drip the alkyl halide in very slowly so that the alkyl halide immediately reacts with the magnesium, and so that we don't get a large amount of coupling product. So depending on how you do your Grignard reaction, you usually drip the alkyl halide in very slowly. But if you think about this, if what I said in the last lecture period was correct, and what did I say in the last lecture period? Oh, that if you form carbon-carbon bonds, if you came up with a reaction to form carbon-carbon bonds in the, late 1800s to mid-1900s, you won the Nobel Prize. You might say, but wait, couldn't we use this Wurtz coupling reaction to form carbon-carbon bonds? For instance, couldn't I say, hey, let's make my Grignard, but then react it with an alkyl halide, do like an SN2 reaction, which it actually wouldn't be if it occurred. It'd be one of those single electron transfer reactions where it undergoes free radical mechanisms, and that's beyond the scope of the course. But you might say, hey, this would be a great reaction to form a carbon-carbon bond and do in essence what we would consider to be an SN2 reaction by having the nucleophile come in and kick off the bromine. Wurtz coupling is a side reaction that's annoying, but when you try and do this reaction for real, it just doesn't work. It's not a good reaction for forming carbon-carbon bonds. Well, people worked around that, and what they found was that if they just added some copper to this reaction, they could actually get good coupling reactions. And so this led to the development of what are called organocuprate reagents, or organocuprate reactions. Your book actually has the specific person's name that's associated with, which I believe is the Gilman reagent or the Gilman reaction. Gilman did a lot of things, and this is just one of them. So if you want to couple two carbons together, what you do is you make what's called an organocuprate, or actually what I call a lithium cuprate. So what we do is we take two equivalents of, let's say, CH3 minus Li plus. So we're going to use organolithium for this, not the magnesium compound, but the organolithium. And remember, we make the organolithium compound by taking an alkyl halide and simply reacting it with two equivalents of lithium to get the Grignard equivalent, the organolithium. You then take 2 equivalents of that Grignard and you react it with 1 equivalent of copper plus 1 chloride. Okay, normally copper's in its +2 oxidation state. You react it with copper 1 chloride. And what happens is that you make a complex where you would have 2, in this case, CH3 minuses. You'd have 2 of those. And then you'd have a copper plus 1 counterion and also a lithium plus 1 counterion. So you have 2 negative ions and 2 plus 1 ions in this complex. And again, we could get into the structures of these and what they look like, but that's really beyond the scope of this course. And I'm not up to date on lithium cuprate chemistry, but there was a long time where people didn't understand the mechanisms of these kinds of reactions. So when you make this lithium cuprate, it turns out that the presence of the copper actually changes the reactivity of the carbanions, and now it turns out that if you added 2 equivalents of an alkyl halide, let's say we added 2 equivalents of ethyl chloride to this. So over here we've got our 2 CH3 minuses, and we've got our copper and our lithium counterions, and we reacted that, we'd have 2 CH3 minuses. If we reacted that with something like 2 ethyl bromides, I'd end up actually forming 2 molecules of propane by coupling the methyl group with the ethyl group of the ethyl bromide. So lithium cuprates are actually very good reagents to do this coupling reaction because the presence of the copper changes their reactivity. And I noticed in your textbook that they said the mechanism was like unknown, and it probably is. The ultimate details are not unknown, but there is probably a mechanism for that. But again, it's beyond the scope of this course. So we can do these coupling reactions for the lithium cuprates. So great idea to try and harness the Wurtz coupling instead of it being a side reaction. We could use it for good, I suppose, but it doesn't work. So what we do instead is we use the organocuprates. We use the lithium cuprate reaction. So if you want to form a carbon-carbon bond between essentially 2 alkyl groups, easy to do with an organocuprate, at least on paper. Okay, so all of these reactions then are what are called organometallic reactions because they involve the reactions of reagents that have an organic portion, a carbon-based portion, and a metal, whether it's magnesium or lithium, or in this case, a lithium and a copper. Now, the last topic I think for today is reductions of the carbonyl functional group. In organic chemistry, we have to define oxidation and reduction, or we normally do this a little bit differently like we did in general chemistry. And if you remember last semester, if you were in the lab class or if you did the yeast reduction of the ethoacetoacetate, we reduced a carbonyl down to an alcohol using the enzymes in yeast. Well, that was a reduction. And so we'll talk about reductions for this lecture, and then we'll talk about oxidations in a subsequent one. So in general chemistry, we had oxidation and reduction being based on gaining or losing electrons. And then we have either the oil rig memorization technique, which I'm not sure I ever know what the oil rig is, but that's not my favorite one. My favorite one is when we talk about Leo the lion goes grr. So lose electrons oxidation, gain electrons reduction. So that's how we keep track of oxidation and reduction in general chemistry. We can still do the same thing in organic, but we'd have to figure out the oxidation numbers of the carbons, and while that's not that difficult, we normally don't do it. So we define oxidation and reduction by sort of an alternative method, which oxidation means that you gain oxygen or you lose hydrogen. And a reduction reaction means that you gain hydrogen or you lose oxygen. It's easier to keep track of whether you're gaining or losing oxygen or hydrogen in the molecule. So that's how we define oxidation and reduction in general chemistry, in organic chemistry. So just to kind of write that reaction out, if you took lab here, at least while I was teaching it, we took an ester and we used the enzymes in yeast to convert that ester down to its alcohol, and in the process we made a chiral center. That was the whole point of that experiment. So we can actually prepare alcohols by reducing carbonyl compounds. And there's two ways to do it. The first would be to think of the double bond, the carbon-oxygen double bond, as if it was a carbon-carbon double bond. How did we reduce carbon-carbon double bonds down to carbon-carbon single bonds? By adding hydrogen. Well, that would go back to last semester, and if you think about it, we used hydrogen and then we used palladium or platinum as the catalyst. Remember, we even reduced triple bonds down to double bonds, but I only want to focus on the double bonds at the moment. So when we reduced our carbon-carbon double bond down to a carbon-carbon single bond, we used hydrogen gas and palladium. Well, couldn't I do the same thing with a carbon-oxygen double bond? Yes and no. Yes, we can use hydrogen, but the problem is that a carbon-oxygen double bond is more stable than a CC bond. And the problem there is that I'm going to need a catalyst that's going to be a little more reactive to make the hydrogen add to the double bond, to the CO double bond. And that's fine because people have found that catalyst. Instead of using palladium, they use what's called rainy nickel. Rainy nickel is just a form of nickel that's very porous so that the hydrogen has a large surface area for the hydrogen to absorb to. But if you use hydrogen and rainy nickel, you'll actually add two hydrogens across the carbon-oxygen double bond, and therefore you'll make an alcohol. Depending on the carbonyl compound you start with, you would make different alcohols. So you would make either a primary or a secondary alcohol. It can't make tertiary alcohols because it can't have a carbon with three alkyl groups still have a hydrogen attached to it. So that's one way to reduce a carbonyl group, is by doing catalytic hydrogenation using rainy nickel. Not necessarily the best method. And the problem is that if I had a double bond and a carbonyl in the same molecule, and I tried to use hydrogen and rainy nickel, it would reduce both the alkene and the carbonyl at the same time, because this is a souped up catalyst to reduce the extra stable carbonyl. And so that souped up catalyst, the hydrogen would have no problems in adding to the double bond. So we'd end up actually reducing both functional groups. So there's another way to reduce just carbonyls, and that's by using this reagent, sodium borohydride. So if I come back here, the sodium borohydride reagent we saw last semester in alkene reactions, because we had the one reaction where we did what? We did mercuration, demercuration, and we added sodium borohydride to that. Sodium borohydride in essence is a borohydride anion where we have a boron that's attached to 4 H minuses. So if you look at this, you would actually, boron is less electronegative than hydrogen is. So each one of these hydrogens has a delta minus charge. And therefore, this is the equivalent of 4 H minuses. 4 equivalents of hydride ion. Well, hydride is a strong base, and it's also a very strong nucleophile. So we can use sodium borohydride to reduce carbonyl compounds in a mechanism that is identically the same as a Grignard. What do I mean by that? Well, if you had a hydride and you wanted to react that with, let's say, formaldehyde, this nucleophile is going to do what? Come in and add to this carbon. Pair of electrons is going to move up to that oxygen. I'm going to end up forming the carbon-hydrogen bond then, have my alkoxide ion. I've got to avoid water in the presence of the hydride because it'll deprotonate it. And so then after the reaction's over there, I'm going to add H plus H2O, and I'm going to go ahead and now form my alcohol. So if I want to reduce a carbonyl only, I'm going to use a hydride as the reagent because it'll attack the carbonyl in exactly the same way as a Grignard did. And I won't bother with the end. Now, we can use sodium borohydride. Where's my extra slides at? We can use sodium borohydride to reduce ketones and aldehydes. So if you have a ketone and you treat it with sodium borohydride, and then in the second step you add then H plus H2O, you're going to form a secondary alcohol. If you react an aldehyde with sodium borohydride and you do your then H plus H2O step, you would end up forming a primary alcohol. Now I have to go back and say, where are we at in the functional groups of alcohols? We're at how do you make alcohols. And so right now, how do you make alcohols? Grignards and now reductions. So if I go back to this slide, Raney nickel would completely reduce a double bond and a carbonyl. But if I only wanted to reduce the carbonyl, I would use sodium borohydride, and that would only reduce the carbonyl. Okay. Now, the question that I would ask is, why won't it touch a double bond? What's hydride? A nucleophile. It's electron rich. What's the double bond? Electron rich. Two nucleophiles aren't going to react. Why does the carbonyl group react? Because the carbon's delta plus and the oxygen's delta minus, so the carbon is now electrophilic. So it has an electrophile to react with. So we've got two of the three possibilities here. We could reduce the double bond and the alcohol all at the same time, or the carbonyl all at the same time, or we can reduce just the carbonyl. Give me another month and a half and then we'll talk about how you reduce just the double bond. But not right now. Okay? So these are great this is a good reducing reagent for aldehydes and ketones. I introduced esters and acid chlorides. I reacted those with Grignards at the beginning of this. Can they be reduced? And if they are reduced, what products do you get? Well, good question. An ester and an acid chloride require you to use a slightly more potent hydride source. You might say, but aren't hydride sources all the same? No. The other hydride source that we can use beyond sodium borohydride is one called lithium aluminum hydride. And lithium aluminum hydride is much stronger of a reducing reagent than sodium borohydride. This is what we would call a mild reducer. This is a much stronger reducing reagent. One time I had a graduate student, when we had graduate students, which was a long time ago, the graduate student was using lithium aluminum hydride to do a reduction, and just it's fairly strong, and he came back and he said, oh, by the way, the bottle of lithium aluminum hydride caught on fire. And this was after the fact, and I'm like, okay, well, what did you do? And he's like, oh, I just poured sand over it. And that's actually what you were supposed to do, because if you add water to H-, it formed hydrogen gas, and the flames just get bigger and bigger. So it is a much stronger reducing reagent, and we would never use this in Organic 2 lab. When I teach Organic 2 lab, we normally use sodium borohydride. So it's a much stronger reagent. It's able to reduce esters and acid chlorides. Now, if you reduce an acid chloride, it turns out that you end up forming a primary alcohol. So you actually end up adding 2 hydrogens to this carbon to form the primary alcohol. And if you react an ester with the lithium aluminum hydride, wait, I didn't want to draw that, then you actually end up forming 2 products. You end up forming the primary alcohol from the part that was attached to the carbonyl, and then you also end up taking this part of the molecule and just basically breaking it apart and forming that alcohol. So esters are a little bit weird in the fact that you end up splitting the molecule apart and forming the primary alcohol, and then whatever the RO group was that was attached to the ester to begin with. Now, I'm going to save that mechanism because I might want to talk about that in class, or better yet, I might want to ask you what you think the mechanism for these 2 reactions are and why we get the products that we do. But for the moment, just remember that those are the products of reduction, and lithium aluminum hydride has to be used with esters, and then ketones and aldehydes are most often used with sodium borohydride. You can use lithium aluminum hydride with ketones and aldehydes, but it's overkill. Okay. Oops, didn't want to do that. Okay, so one more thing about hydrides before we move on to the last quick topic. What happens when you react an epoxide with a hydride? Which carbon do you think the H- is going to attack? If you're saying, I don't know, look at the top of the slide. Strong nucleophile. This mechanism is going to go SN2. The H- is going to come in and attack the least sterically hindered carbon. Pair of electrons is going to move there. So actually you can reduce, we'd have a then H plus H2O step. We actually can open up an epoxide using sodium borohydride in using the H- as the nucleophile, and the characteristics would be exactly the same as the Grignard. The H- will attack the carbon that is least sterically hindered or least substituted. Okay. So that's reduction.